In this module, we will review the basic concepts of probability theory which are needed for modeling and analysis of the reliability of a power system. This is the outline. We will define certain items, then we will discuss the rules of combining the probabilities, and then we will try to illustrate these rules by applications to power system reliability. Starting with the definitions, one of the terms that we normally use is the sample space or the state space. Actually, in the power system reliability work or in the reliability work in general, the term which is most commonly used is the state space. Then there are the events, because we are concerned with the probabilities of the events like failure, events like success, events like the loss of load, and so on. In the events, we will discuss many concepts like union of events, intersection of events, disjoint events, complement of an event, and independent events. All these ideas are useful in trying to combine the probabilities of simple events into more complex events. Then we will discuss the idea of the probability of an event and the conditional probability. Let us start with the idea of the state space. Now, a state space is a set of all possible outcomes of a random phenomenon. In power system reliability, we will say that this is the set of all possible states of the system. If you take a simple example like a generator which is either up or down, then the state space has got only two states, up and down. Let's look at the status of two transmission lines. In the two transmission lines, the various possibilities are that both lines are up, one line is up and one line is down. The line 1 is down and line 2 is up, and both line 1 and 2 are down. So there are four possible states: 1 up, 2 up, 1 up, 2 down, 1 down, 2 up, and 1 down, 2 down. So therefore the state space consists of these four states. Now, events. The events is defined as the set of outcomes or subset of a sample space. For example, if you take the example of the generator, if you pick up the state down, this is the event that the generator is failed. And if you look at the example of the transmission lines, then there were four possible states of this system, and if you pick up state 1 up, 2 down, or 1 down, 2 up, then this defines an event that one line is down or one line is up. Now, how about the combining of the events? So one of the basic ideas is the union of the events. So if you have event E1 and event E2, the union is defined as E1 union E2, and this contains the outcomes from either E1 or E2 or both. Now, if for example E1 is an event that at least one line is up, which is defined by here, at least one line is up, and E2 is an event that at least one line is down, here one line is down, here one line is down, here both are down, then if you take the union, then this will have this, this, this. Now this is common, so we will not count this thing twice. So, and this is again common here, and then we will have this one. So we will have 4 states in the union, which is basically the whole state space in this case. Now how about the intersection of events? The intersection of event E1 and E2 is defined like this, and this contains outcomes from both E1 and E2. For example, if event E1 is at least one line up as before, and event E2 is at least one line is down, now you can see that which states are common, like this and this are common, and this are common. So therefore the event, the intersection of event E2 is, it contains these states, which is one up, two down, or one down and two up, which is that only one line is up. Disjoint events. This is an important concept, and disjoint events cannot happen together because they are disjoint. In the case of the sets, what we say is that the intersection of the disjoint events is null. That is, there is no state in the intersection of the events. Example, if E1 is an event that two lines are up, and E2 is an event that two lines are down, then E1 and E2 are disjoint events. You see that the intersection of this and this is null. There is no state which is common to them. The disjoint events is, as you will see later on, plays an important role in the calculation of the probabilities. Now, what's the complement of an event? Complement of an event is the set of outcomes that are not included in an event. So you have the state space. So if you have an event, then the complement of that is the rest of the state space. For example, if event E1 has two lines up, then the complement in this case, because there are four lines, you take this thing out and you are left with these three states. So this forms the complement of the event. Now you will see that these ideas of union, intersection, and complement, they will translate into the probabilities of these events later on. The independent events. Independent events are those events that happen independently. That means that the occurrence of one event does not affect the probability of the other event happening. So, for example, if you have got a generator and you have a transmission line, and the failure of line 1 and the failure of line 2, failure of the generator are independent, that means that the failure of the generator does not cause the failure of the line, or the failure of the line doesn't cause the failure of the generator. How about the probability of an event? See, a very simple way of looking at the probability of an event is that the number of times that an event occurs divided by the total number of occurrences. So this is really a fraction of the occurrences to the total occurrences when the number of occurrences is very large. Now, there are some basic properties of the probabilities which we have to keep in mind. The first is that the probability of an event is always less than or equal to 1 and greater than or equal to 0. So the probability of an event E lies between 0 and 1. The probability of an impossible event is 0. However, you should remember that the reverse is not true. If the probability is 0, that doesn't mean that the event cannot happen. The probability of a sure event is 1. So these are the 3 properties of the probabilities that we need to keep in mind. How about the conditional probability? The conditional probability is defined as the probability of event E2 given that event E1 is happened and is written like this. So if E2 and E1 are independent, then the probability, conditional probability of E2 given E1 is E2. That means the probability does not depend upon the event E1 having occurred. If the probability of E2 is conditioned on E1 occurring, then the events are not independent. So we will now translate this concept of the events to some simple probability rules, and these are often called as the combinatorial properties of the events. The first rule is the addition rule, then multiplication rule, and then conditional probability rule, and the complementation rule. What is the addition rule? The addition rule is a method of finding a probability of union of 2 events. So, as you know that the union is E1 or E2 or both. So the probability of E1 or E2 are both, and this is given by this formula. The probability of the union of E1 or E2 is probability of E1 plus the probability of E2 minus the probability of E1 and E2 happening together. Now, if the events E2 and E1 are mutually exclusive, then that means that the intersection of E1 and E2 is null. Then the probability of E1 or E2 or both is given by simply adding the probability of E1 and the probability of E2. How about the multiplication rule? The multiplication rule is a method of finding a probability of intersection of two events. That's the probability of event E1 and E2. So the probability of E1 and E2 is given by the probability of E2 given E1 multiplied by the probability of E1. And this is a very basic formula for the multiplication rule. Now, if E1 and E2 are independent, then this one is basically the probability of E2. So therefore, the probability of E1 and E2, when E1 and E2 are independent, is given by the probability of E1 multiplied by the probability of E2. And you will see that this formula is very commonly used in the probabilistic evaluation of the library. Now, how about the conditional probability rule? Now, if an event E depends on a number of mutually exclusive events Bj, then the probability of E is given by the probability of E given Bj multiplied by the probability of Bj and then add over all j's. The complementation rule. The probability of the set of outcomes that are not included in the event can be given by simply the probability of the complement will be given by 1 minus the probability of the event, because this and this have to add to 1. Now, this can be a very useful concept because sometimes it's easier to calculate the probability of E and sometimes it's easier to calculate the probability of E bar. So, depending upon which one is easier, you can first compute either this and then compute this one by this formula or vice versa. Example over here is that if you want to find the probability of success and the probability of failure, let us say these are generally the two kind of events that we are interested in. And if you know the probability of failure, you can subtract it from 1 minus probability of failure to give the probability of success. Or you can find the probability of success and subtract it from 1 to get the probability of failure. You will compute either this or this first, whichever is easier to compute. Now we can discuss the application of these rules to a simple power system problem. And here we will compute what we call the loss of load probability by using these rules. Now let's take the example of 3 generators, and these 3 generators are supplying load. So each of these three generators has 50 megawatt capacity. They have identical probability of failure, which is 0.01, and we can assume that each generator fails and is repaired independently of the others. So the first thing we want to find out is the probability distribution of the generating capacity. Now, if you draw the state space for these three generators, you have 8 states which are possible. You may have all the generators up. You may have one generator down, or generator number 2 down, 3 down, a combination of 2 down and all the 3 down. So all the states are enumerated over here. Now, the generating capacity probability distribution basically means that you find a probability associated with each generating capacity level. Now, since we have got 3 generators, each is 50 megawatts, then there are 4 possible capacity levels. 0, when all the generators are down, 50 megawatt. When one generator is working and 2 are down, 100 megawatt. Then 2 generators are working and 1 is down, and 150 megawatts, where all the 3 generators are working. So we can designate each one of these capacity levels by an event: E0, E1, E2, E3. So E0 is 1 down, 2 down, 3 down. So this means the probability of this event is 1 down and 2 down and 3 down. So here we can simply apply the multiplication rule. Probability of 1 down times probability of 2 down times probability of 3 down, and this will be the value over here. Similarly, you can have capacity level of 50 megawatts, and this event is defined by either 1 and 2 down, 1 and 3 down, and 2 and 3 down. So this means that the probability of this is the probability of this, or this, or this, or any combination. So since these states are disjoint, so we can basically add up the probabilities of these various states, various events, I mean. And how do you find the probability of this? Because this is this and this and this. So therefore you basically multiply the probabilities of these and then add them together. So the probability of E1 is E1 down, E2 down, E3 down, plus this. And the probability of 1 being up can be computed by the complementation rule, that 1 minus probability of 1 down. So when you substitute this and this into these equations, we'll get the probability of E1 is equal to this one. Similarly, you can find the probability of 100 megawatt, and you can find the capacity of 150 megawatt by the same process of multiplication, addition, and ultimately you will get these results. You have capacity of 0 megawatt to 50, 100, 150, and these are the probabilities. As I say over here, this is an example of the probability density function or probability mass function. The left values over here are the discrete random variable capacity. So here the capacity is a random variable which can assume 4 different levels, and these are the probabilities. So therefore this information that what's the probability associated with each value of the discrete random variable is basically the probability density function or the probability mass function. Now let us have the load. Let us say that the load has the following probabilities. You have got 50 megawatt load, 100 megawatt load, and 150 megawatt load, and the probabilities of these levels are 0.2, 0.75, and 0.05. So to compute the loss of load probability, or LOLP, loss of load means that you do not have enough generation to supply the load, which means that some load we will not be able to supply. That means that that load is lost. So that's why we have the terminology loss of load probability. So let us say that even B1 is that load is 50 megawatt, even B2 is 100 megawatt, B3 150 megawatt. Now to compute the loss of load probability, we can say, okay, we will use the conditional probability theory. That the probability of even E, which is the loss of load probability, is E given B1 times the probability of B1. Probability of E given B2 multiplied by the probability of B2. E given B3 multiplied by the probability of B3. Now these probabilities we know. It's like we just have seen that these are the probabilities of the various levels of load. So we substitute these values over here, and now all that we have to do is find out these probabilities and substitute them over here, and we will get the probability of loss of load. So how do we find the probability of E given B1? Remember that B1 is the load of 50 megawatt. So if we have load 50 megawatt, then the only way we cannot satisfy this load is if all the generators are down. Because even if we have one generator up, we can supply this load. So the probability of E given B1, the probability of loss of load given the load is 50 megawatts, is the probability of this event, which we have already calculated previously. For 100 megawatt, the only way we can not supply load is that if 2 or more than 2 generators are down. So that means only one generator is up. So these are the states, and these probabilities we have already found out, so we can use this value over here. Similarly, 150 megawatt, if any generator is down, then we cannot supply this load, so we have loss of load. So therefore we have to use this probability over here. So remember that here it is easier to use the probability of this and subtract from 1 instead of adding all of them together. So that's one application of the complementation rule. So LOLP calculation, we basically substitute in this equation that we had previously the probabilities of these, and we get the probability of loss of load. So you can see that the probability of loss of load is really simple to calculate, and the loss of load probability is probably the most commonly used index in the power system reliability. Now, this example shows that how by the use of simple combinatorial properties of the events or the probabilities, we can compute the loss of load probability. Of course, this system is small. Now, if the system is large, then there are many algorithms which have been developed to compute this thing, but the basic underlying idea is the same.